Okay, let's merge two concepts together. One concept from the previous chapter and one concept we just went over in 12.2. We wanted to look and see what the magnetic force is between two parallel wires. Now, when we think about two parallel wires, we know that they're going to interact. Each wire produces its own magnetic field. We also know that from the previous chapter that anytime we have a wire carrying current, it will feel a force due to a magnetic field. Okay? So one way of looking at this is both wires produce a magnetic field, two magnetic fields interact, creating a force that is attractive or repulsive, or one wire acts as a magnetic source and the other wire feels a force due to the magnetic force. Okay, let's figure this out. Now, once again, we just came up with an expression for the magnetic field due to a wire. The magnetic field due to a wire is mu0 times I. In this case, we're looking at the magnetic field due to wire 1, so it's I1, divided by 2 pi r is the distance between the two wires. So at the location of wire 2, the strength of the magnetic field due to wire 1, which is wrapping around it, is going to be equal to this equation right there. Okay. And again, here's an overhead shot. We can think of that wire 1 is producing a current coming out of the board. Wire 2 is producing a current also coming out of the board. The magnetic field is wrapping around this. If we look at the direction that the current is going, okay, and then, oh gosh, I hate when it's in this direction. Point our fingers in the direction of the magnetic field, the force F equals QV cross B is in this direction. So two wires which are next to one another, each carrying a current in the same direction, are going to feel a mutual force toward one another. Okay? And Newton's third law. For every action there's an equal and opposite reaction. So if I1 pulls on I2, causing it to move this way, there's going to be an equal and opposite force. I1 is going to be pulled toward I2. Okay? Two vectors are going in the opposite direction. So let's take this equation. We're going to combine it with the equation that we got from the previous chapter that says the force on a wire of current, okay, is equal to the current times the length of the wire times the strength of the magnetic field. Okay? So now I'm going to substitute here for B. This becomes my expression. Okay? Again, you know, we have I2L. Now B is going to pop in here. Oops. I2L. Here's B, or B1, magnetic field due to the first wire. And if I move the length to the other side, we get the force per unit length of the two wires, and it's equal to that. So here's the interaction between two different wires due to their magnetic fields. Again, current going in the same direction, we're going to get an attractive force. Current going in the opposite direction, we're going to get a repulsive force.